We want to end this class by making sure that we don't leave you with a scientific nihilist perspective. It is a critical analysis of literature class, and we have certainly given you lots of tools to be critical with. And hopefully enough of a background that you can continue to learn more and more about this if you're interested and use the class as a jumping off point. But we also want to make sure that you understand that science isn't just some sort of waste of designing flawed experiment after flawed experiment. That these flaws, though inevitable, are not catastrophic. That we can take these imperfect experiments and still learn a lot from them. And that we can pile more and more and more evidence until we know something with reasonable certainty, even if not complete certainty. So, when we say that vaccines are safe, for instance, you could point to a flaw or imperfection in every study. However, we have to weigh these against the studies saying that they cause harm, and we have to balance the merits and the flaws of each and come to some sort of conclusion. We call this the preponderance of evidence. Effectively, where does most of the evidence lie? Of course, if something is high quality evidence, it should be weighted much heavier in this calculation than low quality evidence. So much so that one very high quality study can and should outweigh many, many low quality ones. One study can never really be a true preponderance of evidence, so when looking at something brand new, you probably won't really have this. But when looking at something, say, like GMO safety, vaccine safety, or other hot topics that have been heavily studied for decades, we can weigh all of this evidence against each other and start to come to a conclusion. In science, you don't ever really prove anything, but you can get so much evidence for a thing that it can be taken as fact. Actually, evolution is a great example of that. The weight of the evidence is so strong that it can be taken effectively as fact. And of course, there are things with much less certainty, all the way down to true controversies, where we really don't have enough evidence one way or another to decide. I feel like this concept is relatively common sense, and yet it doesn't seem to be applied in a common sense manner. For example, if we think back to the very beginning of class when we talked about GMOs, people latch onto the very few low quality articles showing concern, while ignoring the large number of high quality studies and the large number of meta-reviews showing their safety. And keeping in mind that in some cases, GMOs have the ability to save lives and stop young kids from having disabilities. So this isn't just about some sort of esoteric food development strategy. So why do people do this? Where else do they do this? Pause the video and think about this a bit on your own. If you'd like, you can skip to the next slide and talk about it with your groups before hearing my thoughts on it as well. There's a lot going on here, and it definitely depends on the person or group. In most cases, it's a motivated cognition issue, but that's a really wide umbrella. For some particular groups, being anti-GMO is simply an in-group belief that they'll tend to go along with. Some people just love a good conspiracy, any conspiracy, and this feeds really well into several. For many, it's an appeal to nature fallacy, where natural things are good and unhealthy and lab things are bad. All of these will lead to a motivated skepticism, where they reject trials that show that it's safe, even if they are higher quality than the ones showing the dangers. Another issue that you see in a lot of places is just a severe risk aversion and precautionary principle combined with a sort of trolley problem-like situation. The trolley problem in its simplest form is that if you have a trolley going down the tracks, it's set to hit and kill a group of people. You can switch the lever, moving it to another track where it will kill one person. Do you do it? For a longer version and many other kinds of versions, please Google it and watch or read basically anything that comes up. It's a fundamental discussion of philosophy, and so there's a lot of easy to understand resources on it if you haven't heard of this anywhere. But this comes up in a lot of places, where we are so afraid that something could cause a harm that the good done doesn't counteract the fear of being the people who cause the harm. So even if studies are showing something as safe, there's always ways to point and say, but what about? And continue to move the goalposts of safety indefinitely. So where else does this come up? Well, so many places. Vaccines is obviously a huge one. People are willing to risk a disease that causes terrible amounts of suffering over an incredibly tiny risk of a vaccine. And their reasons separate out really similar to those listed above for GMOs, and even the groups tend to kind of separate out similarly. And there are definitely lots of others as well. So spend some time and talk with your groups some more if you would like about this topic, and then let us know in class if you need any help or you have other things that you want to discuss. I want to give you a quick reminder of something that we talked about way back on the first day of class with reviews. High quality reviews can be invaluable when it comes to sorting through research. Reviews are generally subject to all of the cognitive biases we talked about in previous classes, and of course are only as good as the data going into them. That being said, they can help to undo any one particular experimental flaw by comparing over many experiments. And these are generally written by experts and generally do a lot of the kind of work of sorting through the literature for you. If you need to review the types of reviews, stop back at the earlier video. We didn't spend really any time on publication bias. This class is so packed with so many things that we need basically another year to fully do it justice. But I wanted to mention it quickly as a part of our wrap up. We do need to be careful about publication bias. This occurs when papers with one slant gets published more than another. The most classically accepted example of this is the positive publication bias. And what that says is that it's far easier to publish positive results than null results, even though the null results are also important. One of the tools we have for checking this is called a funnel plot. Funnel plots map the quality versus the results of a study. So low precision studies should generally be more spread out from the center than the high precision studies, which are narrowing in on the center. If you have asymmetries, that can point to a publication bias. They also point to a lot of other things that are listed here on this slide. So it's not a perfect tool, but it's one sort of double check. Another wrap-up comment having to do with a lot of these concepts is that we really need to talk about the misuse of the word controversy. So often, the media will portray things as controversies that aren't. Take a moment on your own or in groups to talk about the following 2 questions. Come back when you've come up with your own ideas to hear mine. Okay, so a scientific controversy occurs when scientists actually disagree because of a lack of clear preponderance of evidence. So these are 3 examples that get talked about as a controversy, but they aren't controversies. Yes, you can find a scientist who will dissent from the scientific consensus, but they are rare, and in most cases, you'll even kind of, when you look into them, they don't seem particularly trustworthy. There's usually something sketchy about it there. Sometimes they're just wrong, or sometimes they just disagree, or sometimes they have a more nuanced view. But more often than not, you'll see something kind of weird when you look into their background. So I've said this before, but trust me, a quack can totally get a PhD or an MD. If someone is dissenting against a huge body of scientific evidence, that's okay, like that happens, and sometimes they're even right, but they need to have some pretty impressive evidence to back up that opinion. If you're going to have that level of claim, you need to have that level of evidence. You can't just have some random theory that you've thought up that you imply that nobody else has been as smart as you and no one else has thought this up. That should never cut it. Okay, so going along with that rant is a related but slightly different rant. And that idea comes up when you talk about what unbiased coverage is. For some reason, people have this idea that unbiased reporting should be 50-50. And I'm not sure where this comes from. Because let's say for a random thing, doesn't matter what it is, that 95% of scientists agree on something, and that 5% don't. 5% have a minority opinion on it. Then to me, unbiased reporting would say that you would give approximately 95% of the reporting time and the argumentative time and the commentary time on the side that 95% of the scientists agree with. And then give a smaller fraction, 5% or some other lower fraction to say, oh, and by the way, there is this small group of people who say this because of this thing, and move on. Unbiased reporting in the sciences should accurately reflect the beliefs of the scientific community. And if the preponderance of evidence is really far in one direction, then that side should get more favorable coverage in order to be unbiased. Hopefully that makes sense. You can tell this is a thing I care about quite a bit. If you have questions, let us know and we can spend some more time talking about that in class, but I'll spare you my ranting here. All right, next up. Okay, so you decide you want to kind of believe in the scientific consensus. Where do you go to find this? So here's a list of some agencies that you can go to when you want to know what the preponderance of evidence in the health science and related fields say. Personally, given how they have played out in the pandemic, I would stick to the medical associations as they're generally a bit more free from political pressure. The CDC and the WHO have become incredibly politicized, and that seems to be deeply affecting their advice. So keep that in mind with any politicized topics. I'll also point out that the CDC prior to COVID-19 has generally erred on the side of extreme caution. So you kind of want to take that into mind when you're saying, okay, well, I'm going to go look before this whole political nightmare that has been the last several years, and I want to look at their recommendations. Just kind of keep that in mind. They do tend to err really so far on the precautionary principle that you have to be careful sometimes that they're not getting crazy with you. Now, with the COVID-19 things, specifically their recommendations around mask wearing and aerosol transmissions, they have been far more on the lack of carefulness side with their recommendations. That being said, they usually, or at least used to, publish all of the numbers that they use to make their recommendations. So you can kind of go in and see if they fit for yourself. If you'd like more if you'd like more discussion on this, we can talk about it in class. I've had examples where I've kind of looked through their numbers and then made value judgments for myself and said, well, I think I'm going to take this risk, or, I don't think I'm going to take this risk. So we can talk about more of those specifics in class. Now, generally, all of these medical agencies follow a relatively similar way of recommending things. And I do generally suggest that you trust them. They tend to have a lot of not just medical doctors, but also research doctors and a lot of kind of MD, PhDs who do both. So they tend to assign committees of scientists to topics, and then the committees review the data and they make guidelines based on that evidence. Of course, they will never be completely free from all the cognitive biases we talked about. Doctors and scientists are human too, but they do tend to be a bit more free from the political pressure because they aren't being hired and appointed by the government. You'll also often see agencies come out and comment on a study if it seems particularly impactful, and those can be really useful. So even sometimes what you'll see is if a journal is about to publish something that they think are going to make a lot of waves in the community, they'll go out to these agencies and ask them for an editorial comment, letter, article, and then that will be published at the same time as the journal article. So this is really common if you have kind of a controversial situation where a journal is about to publish something that goes against the current preponderance of evidence or the current consensus. They'll ask them to look at this and make a comment on it. Most of these agencies do not do their own research, but rather, and what I mean by that is like they're not in the lab doing their own research, but rather they make recommendations off the research that scientists at other agencies are doing. Now, those scientists may actually be a part of the committee. For instance, if someone is an oncologist doing cancer research, they may also sit on the American Cancer Society boards. But the American Cancer Society itself might not really be doing that research. And there are examples where some of these medical agencies do that. Now, this, of course, limits their recommendations to the quality of the research being done. You can't entirely blame one of these medical boards for recommending something done if the research itself is wrong. So as more and better research is done, the guidelines do get updated. So a great example of this, if you want to kind of look into the details of it, is if you look at the AAP's evolving recommendations around introducing allergens to babies and then their safe sleep recommendations. What they recommended for my parents is very different than for me, which is very different for those of you currently in college. And so this is kind of an interesting way to follow how science gets better and how things get updated and how scientists change their mind. And that's really important. Scientists should change their minds when they get better evidence. And that's a lot of times how you really know someone is a scientist, is can they do that? Another wrap-up comment involves the idea of an appeal to authority. This is something that is often talked about as a fallacy. But oftentimes it's really just correctly relying on experts. Knowing the difference, both so that you can use it correctly, and to spot when others are using it correct or incorrectly, is useful. The idea with an appeal to authority is that rather than arguing based on direct evidence, you are arguing based on what authorities say. This can be a terrible thing to do. For instance, if your authority on a topic is Gwyneth Paltrow, or a politician with no scientific credentials. And these are called appeals to a false authority. Often, the only credential is being in a position of celebrity or power. Contrast this to someone saying something along the lines of, the CDC says, or a virologist at such and such respected institution says. Now, to be clear, the authority does not make the argument correct in and of itself. Even experts get things wrong. However, relying on experts for their expert opinion is usually recommended. So let's take masks as an example here. Let's look at a timely example of how appeals to authority can get it right and wrong. Early on in the pandemic, for a variety of reasons, the CDC recommended against mask wearing. The reasons for this seem to vary depending on who you ask and believe, but it was certainly the wrong answer. However, even though it was a wrong answer, it is an appeal to authority that was actually used correctly. Generally, relying on CDC guidelines is recommended. This is, of course, unless you're willing to devote your own time, energy, and effort to become a true expert yourself. Now, as I mentioned before, sadly, due to the politics of the organization at this current moment in time, I might also recommend backing up any of their guidelines by listening to other experts on the topic as well. A few great resources for this is the podcast This Week in Virology, or the podcast The Skeptic's Guide to the Universe, or a blog called Science-Based Medicine. There are, of course, others, but these are three that I tend to trust. Now, later on in the pandemic, the CDC changed their recommendation to wearing masks. This is also an argument to authority if you say that you are wearing a mask because the CDC says so. In this case, it is a correct appeal to authority, and it also yields you the correct answer. Now, with that being said, at basically any point in the pandemic, you could have pointed to a variety of non-expert politicians and celebrities on either side of the mask-wearing argument and said that you were or weren't wearing a mask because of them. This is a case where, regardless of if they got the answer right or wrong, the appeal to authority is incorrect. And I'd like to point out again that none of this is data or true argumentation for making a particular decision. You're simply stating that you're replacing someone else's judgment on the situation for your own. And this is why often, even when appeals to authority are used correctly, they're called out as a fallacy. In a debate, for instance, you wouldn't say that you believe you should wear a mask because the CDC says so. You would want to state the reasons why mask wearing is protective for the public health. With your groups, take a moment and talk through each of the following. Use the examples to help discuss when is it useful or good to use a call to authority, and when is it wrong, and when might it be a good idea, but you have to be really careful. I'm not going to talk about these in the video. We will go through them in class after you guys are done. And here are two more. These are little conversations instead of just one-sentence snippets. The first conversation actually has two competing calls to authority. The second one has just one. Use these to discuss how appeals to authority can be fallacious, even when at first glance it may seem as if the authority has some legitimacy. How can we ensure, when we're using a call to authority, that we're using one that is strong enough to be trustworthy? When should we trust credentials, and when shouldn't we? We've spent so much of this class telling you how science goes wrong. I want to make sure that as our final notes to you, we don't leave you with a sense of doom and gloom about science. Because in these stories of problems and mistakes is actually a much bigger overarching story. That we learn, and we know more, and we get better. We may solve a problem just to create 10 more, and we may make mistakes on our way to the successes. But science is a way of thinking and exploring the world that allows our knowledge to progress. And sure, Some flat earthers may crop up here or there, but that doesn't change the forward march of the scientific body of evidence just because not everyone chooses to participate in it. Science should never be thought of as just this collective, ever-changing body of information. It should be thought of as a process, a way of thinking, a way of doing, a way of exploring. And each of these quotes tells you that in a different way. And one of the things in that way of thinking is that being wrong is never a problem, so long as you're willing to change your mind. And this is really, really an important concept for anyone who wants to do anything. You can't do anything if you are so afraid of failing that it paralyzes you. Experiments go wrong more often than they go right, but when that happens, you learn something from the wrong, and it lets you do even better the next time. I think in an honors class, some of these concepts are especially important to drive home. As a recovering perfectionist, this Marie Curie quote is a reminder that striving for the impossible can be self-defeating. Of course, we want to strive for excellence, progress, and success, but that doesn't involve zero mistakes. It involves lots and lots and lots of mistakes that we can learn from. So why am I driving this home so much to a class where most of you are not science majors? Well, because science isn't just for the scientists. We can all use scientific thinking, reasoning, and logic in our day-to-day lives. Be curious. Research your curiosities. Use the information at your fingertips to answer your questions. Use your questions as an excuse to talk to others. It will make life more interesting. And please, do not buy into your own insecurities telling you that you aren't good at science. As scientists, we do not always package it in a way that is easily sold to college students. But this is a mistake made by science, not a comment on your abilities. We hope that your time spent in this class has made some really current scientific topics a bit more accessible. That you can recognize how to dig into research, judge your authorities and experts, and get help if you need it from trusted sources. We hope that we've given you resources across many areas of science, culture, and literacy to see that science is relatable and interesting and worth learning about. Because even if you never step foot in a lab, you will be asked to make scientific decisions. You'll vote, you'll make health decisions for yourself and your family, decide what memes to forward, and decide what to tell the people around you about scientific topics. Many of you may even go into politics or law and make policies surrounding scientific topics, in which case it is exponentially more important that you can reason scientifically. And of course, so many more applications. And beyond the tools that we've given you in this class, we hope you'll contact us in the future if you ever want to chat more about any of these topics. This is always an amazing class to teach, and we thank you for another fantastic quarter.